we have studied light emitting diode and got to know the non-ideal behavior of a diode is actually the reason behind its operation. But the output of light emitting diode is low intensity beam which is non-coherent and scattered in all the directions. There was a requirement to improve its output. Again and again, we talk about non-coherent, and it should be clear to you why non-coherent is undesirable. Suppose that we have two rays of electromagnetic wave with same amplitude but have a phase difference of 180 degree. Then, when they will coincide at a point, they will eventually die out, which will eventually decrease the output. That is the reason why non-coherent electromagnetic waves are undesirable. Laser is one such modern device which provides highly coherent beam of high intensity light. The operation of laser can be summed up as its full form, but we will see the full form of laser after understanding its operation. It will become easier for you to correlate the full form of laser with its operation. When we talk about the light emitting diode, its working principle is very simple, as in the depletion region, when the electrons from conduction band move to valence band, it emits photon. We have two processes. One is emission and the other is absorption. Emission is directly proportional to the number of electrons which are present in conduction band, whereas absorption is directly proportional to the number of electrons which are present in valence band. One way to increase the output is by increasing the number of electrons in conduction band such that more recombination will take place emitting high intensity light. But this is quite an unnatural phenomena, as you know from the Fermi Dirac function that the probability of finding an electron in conduction band is smaller than the valence band, at least in equilibrium. However, if we introduce a beam of photons, then a huge number of electrons in valence band will absorb photon, making transition to conduction band, increasing electron concentration, and this increased electron concentration in conduction band results in more recombinations, which increases the output light intensity. Absorption is just a way. There can be different ways by which we can increase the number of free electrons in the conduction band. This particular phenomena in which more electrons from ground state are excited to higher energy state is referred as population inversion. Absorption is just a way of creating population inversion, but there can be different ways by which we can increase the free electron concentration in the conduction band. This type of emission is referred as stimulated or induced emission, as we intentionally increase the number of free electrons in the conduction band by different methods for different type of lasers so that more recombination in the depletion region will take place. Now, we can see and correlate the full form of laser, which is light amplification by stimulated emission of radiation. You can see that the output intensity is amplified, and the method by which we have done it is stimulated emission of radiation. Unlike light emitting diode, there are different type of lasers like carbon dioxide laser, helium neon laser, and PN junction laser. For different type of laser, the specific condition or the apparatus used are different. Now if we compare light emitting diode with laser, then for both type of devices, obviously direct bandgap semiconductors are required like gallium arsenide and gallium phosphide. But laser requires specific requirements or apparatus, and all these specific requirements aim to produce population inversion. The conditions or the requirements or the apparatus required for achieving the population inversion for different type of lasers can be different. In light emitting diode, we have spontaneous emission, whereas in laser, we have stimulated emission. The output of laser has high intensity and is highly coherent. Now we are going to focus on only one type of laser, which is PN junction laser. This is an energy band diagram of a PN junction, but the most important parameter is still left to draw, which is the Fermi energy level. And after drawing the Fermi energy level, you can instantly tell What is the specific requirement that is required for constructing p-n junction laser? By observing the Fermi energy level, you can see that the semiconductor used in neutral NNP region are degenerately doped. Therefore, the p-type and n-type region are doped with such high concentration that the depletion region is not at all depleted of charge carriers. The name depletion region is merely for namesake only. The depletion region in this case will be having a huge number of free electrons in the conduction band, which will ultimately facilitate our population inversion. So, degenerately doped semiconductor eliminates the need of photon bombardment, and that is how we achieve the condition of population inversion in p-n junction laser. One important point you have to remember is that obviously there are energy states between conduction band and valence band as well, but these states are not stable states for an electron. That is the reason why the gap between the conduction band and valence band is referred as forbidden band gap. When an electron absorbs a photon, then it may be possible that the energy is not sufficient for make a transition. But when an electron from the valence band absorbs it, it does not know it priorly. Therefore, it appears that an electron in valence band is trying to move to conduction band, but if the energy is not sufficient, then it will come back. The concentration of such electrons is comparatively high. That's why we have a finite probability of finding an electron between conduction band and valence band, but none of these electrons are stable. They are just coming out of valence band and going back to valence band because of insufficient energy absorbed to make a transition to conduction band. The approximate wavelength range for a p-n junction laser is provided as Planck's constant h multiplied by speed of light c divided by band gap energy to hc divided by difference in quasi-Fermi energy levels. We have to consider EC minus EV because this is the minimum amount of energy that a photon can have as a result of recombination which takes place in the depletion region, as the minimum difference in the energy between an electron in the conduction band and an electron in the valence band will be equal to EC minus EV. And we just see that even if there are electrons present between band gap energy, but we do not consider them as these are highly unstable. This range of band gap energy and quasi-Fermi energy levels difference will consist of majority of the photons emitted by electrons after radiation.